In our last video, we introduced three new symbols. So we have an upside down A, which is the universal quantifier, and it can mean for all, or for any, or for every. We have a backwards E, which is the existential quantifier, and it can mean there exists, or there is, or for some. And we introduced the symbol for such that, a common mathematical phrase. This is like a backwards is an element of symbol. So I would like you to take a look at the following statements and write them in symbolic logic. You can use those symbols above as well as other symbols we've had so far, like and, or, not, if and only if you wish. So take a look at these, write each of these statements in symbolic logic, grab some paper and pause, and we'll talk about them together. Okay, our first one is every integer power of 2 is a real number. Integer power of 2, that means for any n in the integer power of 2, that means that n is the power of 2 as the base. 2 to the n is an element of the real numbers. That's how we could write that phrase or that statement, and that is a true statement. Next, there is an integer n such that 2 to the n is equal to 1024. There exists an n in the integers such that 2 to the n is equal to 1024. This happens to be a true statement. 2 to the 10 is 1024. Next, there is a natural number n such that for every real number x to the n is non-negative. There exists an n in the natural numbers such that for any x in the real numbers, x to the n is non-negative, is greater than 0. Is this a true statement? Yes, we know that if we take any real number to an even power, then that's going to be a non-negative number. So let's say like n equals 2. Then x to the n is greater than or equal, or x to the 2 is greater than or equal to 0 for all x in the real numbers. So yes, that's a true statement. Next, for any natural number n, at least one of n and n plus 1 is even. For any n in the natural numbers, at least one of. So at least one of means this is even, or that is even, or both are even, right? So at least one of is always an or. So just make sure to keep that in mind. This and is kind of throwing off the idea that this is logically an or. At least one of n and n plus 1 is even. N is even, or n plus 1 is even, or in theory both are even, which can never be true. So for any n in the natural number, n is even, or n plus 1 is even. And that's our symbol right here for or. Next, we have that for all integers x over 10 is a rational number. For all x in the integers, x over 10 is an element of the rationals. Yes, that is a true statement as well. One quick note, you could have also written this in the form x, an element of the integers, implies that x over 10 is an element of the rationals, and those two ways of phrasing the statement would be logically equivalent. So every universally quantified statement can also be expressed as a conditional statement. So anytime we have for all x in some set, p of s, some statement about s is true, or p of x is true, that's equivalent to x element of s implies p of x. These two things are equivalent, as in this situation. So we could write it in either form. Let's do one more round of these, writing the following statements and open sentences using symbolic logic. So take a look at those, try writing them using symbolic logic, pause the video, and we'll talk about those together. At least one of the sets A and B is finite. Again, recall at least one is or. So we could write this as A is finite. We could write that as the cardinality of A is less than infinity, or the cardinality of B is less than infinity. You could have also written each of those in words. A is finite, or B is finite. Okay, X is an integer, but Y is not an integer. X is an element of the integers, but Y is not an element of the integers. Y is not in the integers. That would be connected by and. It's the case both that X is an integer and that Y is not an element of the integers. You could have also written that as X is an element of the integers, and it is not the case that Y is an element of the integers. Next, for every natural number n, there is a natural number greater than n. For every n in the natural numbers, there exists some other natural number greater than n. So here, while no other variable is included in the statement above, we sort of need to make up some other variable, some other natural number m to compare to n. So for every natural number n, there is some natural number, we're calling it m, in the natural numbers, such that m is greater than n. So that's one way that we could write that using symbolic logic. Lastly, there is a real number a, for which a times x is equal to x for every real number x. There is a real number a, an a in the real numbers, for which, such that a times x is equal to x for any x in the real numbers. And that is a true statement as well. 1 is an element of the reals, and a, or 1 times x is equal to x for every x in the real numbers. This is a true statement. This is a true statement, and these two are open sentences. The truth of these two phrases above depends on, in the first case, what the sets A and B are, and in the second sentence, what X is and what Y is. So those two on the top are open sentences, not statements.